In this video, we're going to look at the analysis of variance. The analysis of variance, or ANOVA, is a powerful statistical technique to allow us to compare the means of multiple groups. If you have two groups to compare, you can use a t-test, but the t-test can't be extended beyond comparison of two different groups or populations. The analysis of variance is more generalized and can compare a number of different populations or groups. What we're going to do in this tutorial is to use one of the built-in data frames in R called insect sprays. So we'll go up my script window here. And now insect sprays appears in my global environment. Let's take a look at the structure of this particular data frame using the stir command. And what we see is we have two columns in our data frame. One is a numerical column, which is going to give the count of number of insects that were collected. And secondly, we have a classification variable, a factor, which has 6 different levels, A through F. If we wanted to find more information about this particular study, we can always ask R. So just using a question mark, and then we'll give the name of the data frame, and up pops some information on this particular data frame. So it tells us where we can find the original data. We can find out all kinds of information about the study by looking at the original Biometrica paper from 1942. But let's go back and take a look at the first few rows of data. With the head command. So on the left side we see the count of number of insects, and you can see there's replication because on the right side we have the spray. So there are a number of different replicates for each of the 6 different sprays that were used in this study. I always like to start an analysis of variance by looking at the means or the medians of the different groups in my data set. So what we can do here is a very simple sort of plot. We look at some box plots. So we're going to look at count as a function of spray, and we need to tell R what data frame we're using. So it's the insect sprays. And then here's my little box plot, that a series of box plots that show up in the graphics panel here. So what you can see is that there are obvious differences in the number of insects associated with sprays A through F. Just to give you a little bit of background on a box plot, the strong line in the middle represents the median of the distribution. This upper part of the broad box represents the 75th percentile. This lower bound is the 25th percentile. So 50% of all of the values fall in this middle region here, the so-called interquartile distance. So 50% of all the values are going to be found inside the box. From here on up, we have the top 25% of the data, and from here on down is the bottom 25% of the data. So you can see just by looking at the medians that it looks pretty clear that there are differences among the different sprays in terms of their effectiveness at killing insects. We can use analysis of variance to actually demonstrate those differences. So what we're going to do is just to call AOV, that's the function to do an analysis of variance, and our call is going to be very similar to the plot command that we have just up above there. So and I run that, and I get a little bit of information here. I get some information on the sum of squares and information on degrees of freedom, but I don't really have a whole lot of information here that tells me whether or not there's a significant difference among those means or not. what I need to do is to save my analysis as an R object. So I'm just going to call my object ANOVA1, and we'll save that, and it appears now up in my global environment as a value. Now what I can do is to call summary on my saved analysis, and now I've got some more useful information. So what we see here is what is called an F-test, and the F is a proportion or a ratio of the mean square error that is associated with the spray divided by the residual error, the error that can't be explained by the spray. And so you can see this value, 533 divided by 15, is this F value here. It's very large, indicating that we can explain a lot of the variation by just knowing what the spray is. And in fact, that is clearly evident if we look at the p-value. So the p-value is the chance that the differences that we see over here in our box plots, that those differences arose simply by chance. And because this p-value is so very small, then we can say the odds of the observed relationships occurring simply by chance, virtually nil. In fact, we see that the p-value is denoted with 3 asterisks, which indicates that p is less than 0.001. But we still don't know which spray is different from the next. So what we can do is to do a series of pairwise contrast. We can compare spray A to spray B, spray A to spray C, and so forth. And to do that, we use a test developed by a famous statistician named Tukey, and the HSD stands for honest significant difference. And so all we need to do is to call Tukey HSD and just to give our summary there, and we get all these comparisons. So what this particular output is showing is comparing B to A, C to A, D to A, and it continues on down until we compare F to E. So what we're interested in is, well, you can see the difference between B and A right here. So the difference is 0.8333, and the LWR and the UPR give the upper and lower bounds for the differences, the statistical differences between those two groups. And so you can see that varies from a negative number to a positive number. In other words, it overlaps 0. And if they overlap 0, then that means that our 95% confidence interval in here is going to overlap the region where there's no difference. And so we can see that's clearly the case because our p-value is almost 1. In other words, we can't claim that there's any sort of statistical difference between A and B. And we look at the data there, and you can agree with that just by eyeball. But if we compare C to A, then C has a very low median and a low mean, whereas A has a much larger one. And here we don't have any overlap. Minus 17, minus 7, that's the lower and upper bound. That does not include 0. And in fact, the probability that those two means are different is virtually certainty. The p-value goes out to 0, out to 7 decimal places or so. So we can do that for every one of these combinations, C and B, D and B, so we can figure out which ones are significantly different from the others. So our analysis of variance allowed us to see that there were significant differences. That's what this analysis here told us. There are significant differences among the different sprays, but it doesn't tell us where those significant differences are. To find that, we need to do pairwise contrast, and we're going to do that by calling the Tukey HSD function, and that allows us to do pairwise comparisons. And by the way, the analysis of variance can be extended to more than one factor. So what we have done here is called a one-way analysis of variance, and the one is simply the type of spray. But you could imagine a situation where you do an experiment where you give plants high and low levels of fertilizer and also shade some of the plants and don't shade others. So you have two different factors, and we could put both of those factors into our analysis of variance as well. And that can be extended, of course, to more than two. But the example I gave with the shade and with the fertilizer would be referred to as a two-way analysis of variance. And similarly, add a third factor and you've got a three-way analysis of variance. So it's a highly generalizable technique and a very powerful one.